Hi guys, welcome to the lesson of partial differential equations. So previously we discussed uh, linear and semi-linear partial differential equations of first order, and we saw how to solve the problems. Now in this class we are going to talk about quasi-linear partial differential equations of first order. So the general form of quasi-linear differential equation, in fact partial differential equation, is f of xyz times this partial of x, and then g of xyz times this partial of y equals to some function of xyz. So we have a problem here that y times partial of x plus z times partial of y equals 2y plus z is given equation, and the initial condition is zx comma 0 equals 6x. So to solve these kind of problems, first we need to construct the Lagrange form as usual. We did in the previous lessons. So it's dx over y, because the coefficient of the partial with respect to x is y, and then dy over z, and then it's equals to dz over 2y plus z. Now to solve these problems, what we do here is simply we say that if dx over y equals dy over z equals dz over 2y plus z, then we can say that dx over dt equals y, dy over dt equals z, and dz over dt equals 2y plus z. And then we can see that now this is nothing but it's a system of linear first order differential equations, right? And then for initial conditions, we can just change it into the form s comma 0. We can write it in the form of s. So now the problem is converted from xy to s 0, right? So here we have this x comma 0, which represents x and y. So here we represented x as s, so it's s comma 0 equals 6s, where this thing 6s is nothing but it's z, and this s is x, and this 0 it represents y. So the initial conditions are constructed in the way that x of 0 is s, this component, y of 0 is 0, this component, and z of 0 is 6s, this component. And we can solve this system of differential equations by using eigenvalues and eigenvectors. So it's easier if we can do that. Otherwise, we can also use Laplace transformation techniques because it's initial value problem. Else we can use the operator D method as well. So this is the form in which we can write the differential system of differential equations, where this matrix is called matrix A, this is called capital X, this is called x prime, so x prime equals ax, and then we can find the determinant of this A minus lambda I matrix to find the characteristic polynomial, which is this thing here, lambda times negative lambda squared plus lambda plus 2. And by constructing, so we get the values of lambda. So we have three, it's a cubic polynomial, so we have three eigenvalues. So here we can just find the corresponding eigenvectors by using the techniques of finding the eigenvectors I write here directly, but you can just compute or you can use calculators for that purpose. So for lambda equals 2, we have this eigenvector 1 over 4, 1 over 2, 1. But for our ease, what we did that we multiplied it by 4, so we get 1 to 4. Because we know that eigenvector uh, is simply, it is a non-unique vector for this single value. So we can construct many eigenvectors by simply multiplying it by the scalar number. So here we multiplied it by 4 to make it easier to take it out from the fractions. And so for lambda equals -1, we have this vector. For lambda equals 0, we have this vector here. So this is for lambda equals -1, this is for lambda equals 0. Then we can write the solution in this form, that xyz equals c1 times the e to the power of the first eigenvalue times t times this eigenvector that is corresponding to the eigenvalue lambda equals 2, then plus c2 times e to the power the eigenvalue that is lambda 2, so it's -1, so it's -1 times t, and the corresponding eigenvector plus C3 times e to the power 0, because the third eigenvalue is 0, and times the corresponding eigenvector. And then we applied the initial conditions. So here x of 0, y of 0, z of 0, and c1 e to the power 0 times this vector, c2 e to the power 0 times this vector, plus c3 times this vector. It's equal to the initial conditions, that is x of 0 is s, y of 0 is 0, z of 0 is 6s. And then simply we can construct this system of linear equations, and we can solve it for c1, c2, and c3 in terms of s. So we get from here that c2 equals 2c1, which implies c1 equals, so equation 3 implies 6c1 equals to 6s. This implies c1 equals s, c2 equals 2s, and by putting these values in equation number 1, we get c3 equals negative 2s. And then we can just put these values in place of c1, c2, and c3 to get the desired result, but it is in the form of parameters s and t, so we need to convert back into Cartesian form, that is in form of x, y, and z. So what we will do here, we will simply do some algebraic manipulation. So let's call these equations, it's equation number A, it's B, it's C. So by B plus C, that is y plus z, this one and this one, adding this one, this 2s and this negative 2s e to the power negative t, these will cancel out, and we're left with 6s e to the power 2t. So we can write e to the power 2t equals y plus z over 6s. And then also we can write from here simply that s, or we can write s e to the power et. We can write it here that s e to the power 2t. We will use this result later in our solution. So it's equals to y plus z over 6. Again, from here, we can use that s e to the power negative t. It's equals to z minus 2y over 6. So we will use these results in the later stages. And here we can see that e to the power negative 2t. From here, if you flip this thing, or you change the power, so what we need to do is we need to take the reciprocals here, right? So e to the power negative 2t is, sorry, from here, we see the power negative t. So we squared both sides. We squared both sides to get this result, because it's e to the power negative t. And if we square both sides, so we'll get a square on the right and left side. And then again, if we flip these, so we'll get e to the power 2t equals 6s whole squared over z minus 2y whole squared. Now we can compare this result with this result here, because both are in form of e to the power 2t. So we can compare the results. So we call it alpha, and add this one alpha, and this one is beta, and we compare these two components. So we get the result that 6s is equals to this thing by the simplification, and then s equals this thing. So now these results we can use in our any of the equations. So I will take equation for this equation, that is x equals s e to the power 2t plus 2s e to the power negative t minus 2s, and plug in the values for s e to the power 2t, that is this value, s e to the power 2t, and s e to the power negative t, this value. And for s, we have this value here, this one. So we'll plug these values. So x equals s e to the power 2t. So s e to the power 2t is this thing. And then 2s e to the power negative t. So this is 2 times s e to the power negative t here. We have constructed this s e to the power negative t equals z minus 2y over 6. And s e to the power 2t equals y plus z over 6. Now we can just simply, and then it's negative 2 times s. So negative 2 times s is, here we have s, so we can plug in here s, the result of s, and then by simplification here, take LCM and just simplify, and we'll get the desired result is x equals to this thing. And further, if you want to simplify it, we can just do it like this. It will be 2x plus y minus z equals negative 2 over 3 times y plus z squared times z minus 2y squared. Sorry, this is not squared. This is not squared. Whole power 1 over 3. And if we change the signs, okay, so this is minus z. Minus z. And if we want to write in terms of z, we can write z equals, and so this is negative, and to make it positive, this will be negative, so it will be 2x and plus y plus 2 over 3 times y plus z times z minus 2y is squared power 1 over 3. And we can verify the condition and the equation as well. I'm just verifying the condition here. So z of s comma 0, that is, we can also write z of x comma 0. So z of x comma 0, it will be 2x plus 0 plus 2 over 3 times 0 plus z is 6x times 6x minus 0 is squared power 1 over 3. So this is z of x comma 0 equals 2x plus 2 over 3, and 6x times 6x is squared is 6x cubed. 1 over 3, this will cancel with this thing, and 3 times 2 is 6, so z of x comma 0 equals 2x plus 4x, that is equals to 6x. So you see the initial condition is verified, and we can also verify the equation by just taking the partials with respect to x, y, and then plugging in the equation to verify. So hope you guys will understand this lesson and the steps that are required for solving a quasi-linear partial differential equation of order 1. That's all for the time being. Thanks for watching the lesson, and we'll meet in the next lesson with some more topics. Thanks and goodbye.